Hello everyone, we are in the week 4 talking about interlayer bond strength and hardened state characterizations of 3D printed concrete. In the previous session, we looked into the definition of interlayer bond strength and how it's formed and the consequences of it. Let's dig into more about interlayer bond strength and lack of fusion by considering potential factors influencing interlayer bond strength and the lack of fusion. Several factors that potentially impact interlayer adhesion, namely material type, inclusion of fibers, material rheology parameters like R-thix or A-thix, accelerated materials affecting setting times, printer settings such as pass time, printing speed, object geometry, nozzle to layer distance influencing pressure and intermixing, filament layer height, printer size and the resulting material transportation distance and rheological flow, nozzle type shaping, and lubrication layer and contacting area between the filaments, environment condition during and after printing, type of concrete mixing, which are the batch versus continuous mixing. Among these, some exert significant influence while others are more minor. Let's discuss the 4 most influential parameters, which are surface moisture, air entrapment, thixotropy, and surface roughness. I must highlight that this work was explored and suggested by a researcher, Dr. Kruger in Stellenbosch University. The first parameter, surface moisture. The most prevalent cause of lack of fusion in 3D printed concrete is a loss of surface moisture following extrusion during the pass time. After extrusion, water evaporates from the concrete filament surface, a process influenced by factors like temperature, humidity, and wind speed, making the surface drier and less flexible than the succeeding filament layers. As a result, the lower layer absorbs water from the newly deposited top layer, expelling air into the layers and increasing interlayer porosity and permeability. Water migration from newer to older layers affects cement hydration, leading to increased anhydrous cement content over the interlayer region, contributing to the lack of fusion. A longer pass time heightens water evaporation, intensifying water migration, increasing lack of fusion. This concept aligns with the setting time in conventional concrete pouring to prevent cold joints, where initial water evaporation stops after the setting time, affecting the material's chemical structure irreversibly. A study performed by a group of researchers investigated how surface moistures affect interlayer bond strength in printed concrete. Shielding the first layer from drying showed minimal interlayer bonding strength reduction up to 2 hours, whereas exposed specimens displayed significant interlayer bonding strength reduction, especially within the first 10 minutes. Another study group found a 75% interlayer bonding strength reduction within 60 minutes, mainly due to the surface moisture loss. A research group of Swinburne University's study showed interlayer bonding strength reduction from 0 to 20 minutes, but increased at 30 minutes, attributed to bleeding water rising from the surface. Another influencing factor could be the concrete mixing method employed, batch mixing or continuous mixing. Batch mixed concrete aging during printing results in lower surface moisture due to early hydration, potentially weakening IBS. In contrast, continuous mixed concrete maintains more surface moisture at all times since its age is decoupled from the print duration, unlike batch mixed concrete kept dormant in the hopper for extended periods. Reported frequently in literature, the presence of large elliptical or longitudinal type cavities in the layer regions is a notable observation. According to a research group in Dresden University, these voids form due to air enclosure. So when the upper layer interacts with uneven substrate caused either by surface roughness from exposed aggregates across all layers or prolonged pause time leading to surface rigidity and voids in all the layers. This process traps air during extrusion and placement. Affected by material rheology printing speed, nozzle to filament distance, extrude shape, and potential print head by vibration. The existence of macro pores in interlayer region diminishes the bonding between the filaments, reducing mechanical or interlayer bond strength. Void formation between printed concrete layers was studied by another researcher, and their study reveals that most core specimens exhibit 3.8% voids, while poorly printed concrete showed 4.8% compared to well-printed concrete with 1%. Mold cast concrete had more small voids, like 0.2 to 1.6 millimeters, compared to printed concrete. Poorly printed concrete had much more larger voids, like 1.6 to 4 millimeters, mostly between filament layers. By enhancing print path and mechanical material rheology, well-printed for the case of well-printed concrete specimens, they notably reduced air voids across the entire size range. A research group from Nanyang Technical University also linked reduced IBS to macropores in interlayer regions. They introduced overlay compaction as a countermeasure to the macropore formation, a technique involving optimized print parameters like speed, nozzle distance, layer height, and extrusion rate to exert substantial force during deposition. This leads to quasi-compaction of the substrate layer, allowing more interrupted air to escape and enhancing physical and chemical bonds between filament layers. By reducing the standoff distance from 20 mm to 15 mm, while keeping all the parameters constant, they achieved a 33% increase in IBS. Optical microscopic images depict the reduction in macropores between filament layers, showing improved bonding with adjusted standoff distance. The authors emphasize that bond strength is related to the substrate's yield strength or viscosity, increasing with longer pause time. High yield strength might stiffen the interface, hindering intermixing with subsequent layers. So one of this figure illustrates increased macropore between layers with longer pause time, corresponding this mechanism that I explained before. The third parameter is the factor is the thixotropy of the material. The filament layers can create bonds through intermolecular van der Waals force via thixotropy if the pause time is relatively brief. This is notably applicable for 3D printed concrete material designed to exhibit thixotropic behavior, aiding pumping, extrusion, and construction. A researcher, Kruger, and his team devised a bilinear thixotropy model specific for 3D concrete printing, where the process involves a deflocculated microstructure upon material exit from the nozzle, which represent the dynamic yield shear stress due to pumping-induced shear action. The material then reflocculates to its original state before agitation, symbolized by the initial static yield shear stress of the material. The reflocculation time spans up to an average of 5 minutes for highly thixotropic materials, although this duration varies among materials. Following reflocculation, microstructure structuration occurs, marked by the formation of early hydration products like ethylene guide needles, fostering pseudo-thixotropic behavior. Notably, this involves a chemical, not physical, bond, unlike the reflocculation mechanism seen in materials like ketchup, paint, and detergent, which rely solely on physical bonds. Research by the Professor Ruzel highlighted the thixotropy in self-compacting concrete could lead to distinct layer cost, causing a potential reduction of over 40% in structural mechanical resistance. If the initial concrete pour structure rates too much after placement, resulting in increased apparent yield stress, subsequent pour may fail to blend entirely, creating a weak interlayer interface. To counter this, the author proposed using low thixotropy material, ensuring that the structuration rate remains below a critical value depending on the time interval between the pourings. However, a researcher like Keita suggests that the decline in bond strength between printed concrete layers isn't linked solely to thixotropy, but primarily to the localized drying of the initial resting layer, a factor interconnected with the thixotropy. Accelerating agents tend to increase the structuration rate due to their chemical nature. Professor Rizal notably augmented the structuration rate of the reference mix by 10-fold by adding a 3% accelerating agent by cement weight, illustrating a strong correlation between A-fix and the material setting time. Dr. Kruger delved into the impact of reflocculation on interlayer bonding strength with nanomaterial additions. Tests had held a consistent 12-second pause time between layer deposition. Their findings suggested that increased thixotropy behavior correlated with improved IBS. However, these results might be influenced by microstructure densification, common in cementitious material with nanoparticles. While insightful, this study calls for further research to validate the presented theory. It is hypothesized that batch mixing may hinder thixotropic bonding between filaments at longer concrete ages or print times. With concrete age links to elapsed print time, the concrete in the pump's hopper loses free water due to early age hydration products formation, limiting the medium available for particle reflocculation during extended printing, possibly impeding the efficacy of the thixotropy mechanism. Continuous mixing is envisioned to yield better outcomes in the context. The last factor, the fourth factor, is the surface roughness. The interaction between printed filaments and the substrate is significantly impacted by surface roughness, constituting an essential mechanism. A researcher, He et al., examined the bond strength in conventionally cast concrete repair systems, emphasizing the influence of increased surface roughness on mechanical interlocking between old and new concrete. Enhancing artificial roughness improved the multiple mechanical properties, including tensile splitting strength, flexural strength, and directional tensile or bonding strength. A study by van der Putten explored the surface roughness of printed concrete filaments at different printing speeds using precision laser technology. Lower speed, like 1.7 centimeter per second versus 3.0 centimeter per second, significantly raised surface roughness in the print direction by 144%, while in the transverse direction, the increase was 48%. Mechanical strength achieved at 1.7 centimeter per second consistently surpasses those at 3.0 centimeter per second speed. That underlining the substantial role of surface roughness in improving interlayer bond strength. They attributed the inverse relationship between print speed and surface roughness to induce shear stress during pumping, and varying speed and associated kinetic energy. ImageJ analysis reveals spatial differences in sand particle distributions for both speeds. Both speed, then at 1.7 centimeter per second, the volume of sand particles within the initial millimeter depth of the filaments was greater than at higher speeds. However, beyond 2 millimeter depth, sand particles increase for the higher speed, likely linked to the formation of the lubrication layer or slippage layer during pumping, typically about 2 millimeters thick. This lubrication layer results from hydraulic pressure gradients within the concrete during pumping, causing flow-induced particle migration and separation of water from the fine paste. Larger particles tend to move away from the walls towards the pipe center in what's termed plug flow. Hence, in case where a lubrication layer exists during printing, especially prominent at higher speed due to increased pumping pressure, smaller particles may migrate towards the surface of the wall of the pipe, potentially resulting in a smoother surface finish detrimental to achieving adequate interlayer bond strength. Moreover, as more free water separates from the fine paste to form the lubrication layer, a higher water to cement ratio might exist within it, so ultimately leading to increased air content in that region once it hardens. So today's session concludes here. While these 4 parameters hold significant influence, several other minor factors likely contribute to lacquer fusion. Both structural designers and site engineers need to consider these variables or parameters to mitigate the lacquer fusion issues. In the upcoming video, we'll delve into mechanical testing techniques used to assess interlayer bond strength and the resulting orthotropic behavior. Thank you for your attention, and I will meet you in the next video. Bye for now.